Okay, we'll first review the secant method, which is used for minimizing a univariate function. So we have a function f that is from R to R. So it has just a scalar variable. And we're trying to say find a minimizer of this f. And the secant method is to iterate the following. So suppose we're given two initials, call them x0 and x1. So given these two initials, we can apply this secant rule or the secant up rule. So we get the next xk. Say for example, in this case, if I have x0, x1, the next one we're trying to get is x2. So x2 will be equal to x1 minus this, just x1, x0, and this is f prime at x1, f prime at x0, and f prime at x1, f prime at x0, and then simplify this, and eventually you get that. Right? This is our secant, the update rule for the secant method. Okay, so given x0, x1, you can compute x2, and then you use x1 and x2, you can compute x3. So that's the secant method. And so if I summarize everything that we need to do for the secant method, I write everything here. So the secant method requires the input as follows. So it needs to know how to compute the derivative of f, right? As we see in the update rule, we need to repeatedly use the derivative of f at the given iterate. So we need this f prime. Then we need two initials, and this k is the maximum iteration number, and this epsilon is the tolerance for the stopping. So you'll see this too later on. These are artificially set parameters for your algorithm. So for the secant method to work, in the first step, since we're given these two initials, then we're going to compute their derivatives, the derivative for f at these 2 points. So we call them g0 and g1. So the g0 is the derivative of f at x0. g1 is the derivative of f at x1. So this is the why that we need to know how to compute the derivative of f at any given point. So this is actually a function that we need to give to this secant method. So you got this g0, g1, and then you can start iterating the secant using the secant method. So let k be the iteration number. Then for k equals to 1 to up to k minus 1, which is the maximum iteration number you set. And then this x, the update x, is equal to, recall the updated rule for the secant method is this, where the gk means the gradient of f at xk. So this is the update rule just reviewed. So you can compute the next point x using this formula. So now, since we have x0 and x1, we'll have their gradients or their derivatives, g0 and g1. So we just need to plug in. So we have this as x0, then this will be g1 minus x1 g0. And then on the denominator, we have g1 minus g0. Okay, so you have all this, then you can compute the next point, which is this x. And once you have this x, you can compute its gradient, which is just apply the f prime to to x, and just apply f prime to x, evaluate f prime and x, you get this g. So now you have the next point, which is this is like the xk plus 1. This is like the g of gk plus 1, which is a gradient f or derivative of f at xk plus 1. And we set this stopping criterion here is to check if we're not making much progress, then we can stop the algorithm, right? So how do we check? How do we mean by not making much progress? So you see that we previously have x0, x1. So let's say look at x1. Next point will be x2, which is the one we just computed, which is this x. So you look at the difference. the difference divided by x1, this is called a relative change. So the relative change in your iterates, if it's smaller than epsilon, which is the number that you set at the beginning, then you will terminate the algorithm, you terminate the loop. Okay, that means you do not really finish, even if k is still far away from the big K, you will still stop because you think that you're not really making much progress. All right, so this epsilon is what is customized. You can set it, for example, you can set it to 10 to negative 10, 10 to negative 2, which means that the relative change is less than 1%, or 10 to negative 3 if you want to be more accurate. Okay, so this is what you set. This is one of the parameters you need to give to this secant method. So once we check that, and if it works, if this is satisfied, then you terminate the algorithm. But if it's not satisfied, then you just continue. You will repeat this procedure. And before repeating it, remember that right now you have the new xk plus 1, right? This is your x here. Okay, you get the new x. So now you're going to update. Your x0 should be the x1, and your x1 should be this new x. Okay, so you set your x0 to the x1, and then you set your x1 to this new x, which is the one you just computed here. Remember that you cannot reverse this 2. You cannot change this 2. Okay, you cannot change the order of this 2, because once you change it, then you assign the value x to x1. Then you assign x1 to x0. Eventually, both x1 and x0 will be equal to x. So it's not correct. So you have to update the value of x0 first, and assign the value of x1 to the value of x0, and then assign the value of x to x1. So in this case, it's like the x0 will be this x0 will be this value here, and this x1 will be x of k plus 1. Okay, and then you can also update their gradients. The derivative of f at x0 will be just the derivative of f at x1, but that was the g1. So you update the g0 to g1, and also the g1, you update the g1 by this new g you just computed. Okay, so in this case, as I said, this is essentially the xk. This will be xk plus 1, and this will be f prime at xk, and this is the f prime at xk plus 1. And then you move to the next iterate, and you're using these 2 points, xk, x plus 1, to compute xk plus 2. So that is in the next iteration. Okay, so as you can see, then you just repeat this, and either this stopping criterion is satisfied, the relative change is small enough, and you terminate the algorithm, or the iteration number has reached the maximum iteration number you set. You can set to k to say 100 or 200. It's up to you. And either way, the algorithm will stop. And once it stops, they will compute. This is the latest one they computed. I will just output this as the minimizer of f. Okay, so this is the secant method. So when you implement this, you need to just follow these steps. The implementation of the stabilization method using Python. So you can use any kind of editor that you like. I recommend doing this in Anaconda, or if you like, you use others as well, but this doesn't really matter important. It's important that you can get some highlights, in syntax highlights that can make your coding slightly easier on eyes. Okay, so to implement the method, I need to create this .py file. So here I put the code inside this algorithm.alg.py file. And once we put it in there, this is like a completely text file, right? So text file that is ending with .py, meaning that it's a Python script. So this is the algorithm.py. So this is my first row. I write this import numpy as np. So numpy is a Python package focusing on numerical computations. So This is NumPy, and I use this means that I later can call the functions inside this NumPy package, and I can just name that as np dot the function name. Okay, so that's the I first import this, and then I'm going to implement the secant method. The secant method is the one we just reviewed. Try to find the minimizer. The secant method is try to find the minimizer of a univariate function, or function f, where this f is a mapping from R to R. Okay, and to implement this method, we need to know the derivative of f, and we also need to. The derivative of f means that we need to know df as a function, and we plug in any variable, any value into this df, it will output a scalar as the derivative of f at a given input. And we need two initial guesses, we call them x0 and x1. And then eventually we'll return this x as the output, which is the minimizer of f. Okay, and for stopping criterion, I set two of them. One is, so the iteration will stop when either the maximum iteration number is reached. I use its maximum underscore iter as the maximum iteration number. And another stopping criterion was set is the tolerance for the relative change. The tolerance is named as TOL. Okay, so that is this part is a description of the algorithm. It's not really explained executed, as you know that this is within this notation. This is just some comments. Okay, so this is my algorithm. First, I need to define this secant method. I need to wrap up this algorithm into this name. I call it secant, and I know that I need to give the input df, which is derivative of f. This is the function that I need to define for, and I need to define it and input it into the secant method. And I need the two initial guesses, x0 and x1. I need to give the maximum iteration number, so I set the default maximum iteration number to 100. And you can set to others if you like. The tolerance is set to 10 to negative 3. So this is the tolerance for the relative change. And to implement this, I need to compute the g0, g1, which are the derivatives of f at x0 and x1. So I need to apply the df to x0, df to x1 to get this g0, g1. So these are two scalars. The derivatives of x0 at x0 and x1 are with here. And next, this is the main loop. I need to run the iterations. So I use this for loop where this k is the iteration number. For k in this range, this means that the k will run from 0 to maximum iteration number minus 1. So default is this one, but if you input others, it will be just the number minus 1. So in total, you will run this k for maximum iteration number. Okay, so this is the main loop. And the key step for the secant method is this. Right, this is you update the x using this formula, secant update rule here. Okay, and then you compute the f prime. You compute the gradient derivative of f at this x. So the g will be just df applied to x. Remember that df is the function that you as the input of the secant method. And next, I will do this one of the stopping criterion. We'll check one of the stopping criterion. We'll see if the relative change of x is small enough. So to do that, I need to evaluate the absolute value of x minus x1 divided by the absolute value of x1. So absolute value is a function in the NumPy package that we defined earlier. As I said, the np will call the NumPy package, as I use this as a shortcut for NumPy. And then I also have this ABS. This is the one of the functions under this NumPy package. So there are many other functions under this NumPy package. You can search online for the functions. The most of the algebraic computations they are implemented as functions under this NumPy package. So this gives me the ratio. And if I check the ratio, if the ratio is less than the tolerance, then I will break this loop. That means we jump out of this loop, but we do not really finish this k, even if it's not the maximum number yet. Okay, so that's the this is to check the one of the stopping criteria, and then if it's satisfied, then as I said, we will break out of this loop and we'll directly return the x, the current value x that we computed here. But if it's not satisfied, then we'll continue the computation. We'll update x0, x1 as we showed in the slide earlier, and also we'll update their derivatives, g0 and g1. And once I finish this, then this algorithm, after finish this step, as the loop will repeat itself and compute this. But remember that in the previous iteration, we have done this update. So this x0, x1, g0, g1 will be the updated ones of this. So it will be the new x, which will be corresponding to the xk, xk plus 1, and the gk, gk plus 1. Okay, then we'll repeat this. Okay, so after either this one is satisfied, or we run to the maximum number of iterations, then this for loop will terminate, and then the x will be our output. So this is the secant method. Okay, now let's consider the steeply descent method. So steeply descent method is used to find the minimizer of this multivariate function. So I have this function f is from Rn to R. So n can be pretty large. So now this is different from the secant method that is only applied to univariate functions. So this x is the argument of f is actually a vector. So what our goal is, we try to minimize this function f to find the minimizer of f, and find that the best minimizer here. Okay, so to implement the steeply descent method, we know that steeply descent method is one type of gradient descent method, which use next gradient as the descent direction, and use the alpha k, use the step size like this as the alpha k for the update. So the general gradient descent method is to implement xk plus 1, xk minus alpha k, gk. So where this xk is the current iterator you have, this gk here is the gradient f at xk. So you need to compute the gradient of f at this xk. Then you find this alpha k. You find this alpha k by minimizing this right hand side. So alpha k is the minimizer of this, and then you put this back. Once we compute this alpha k, you put this back here. Then you can get the next xk plus 1. So this is the step that we're going to do. Initially, you have the x0, which is the initial guess you have, and then you try to do this iteratively to find the minimizer. Okay, so this is the algorithm. The steeply descent algorithm, we need to know how to compute the gradient f. For every given value x, we need to know how to compute this gradient f. So this will be a function as the input for gradient descent method. And the x0 is your initial guess. You can set it to anywhere you want. This k is the maximum iteration number. You can also introduce the tolerance as the another stopping criterion. And for simplicity, I just put it here. Later on in the code, I will show how to add the other one, which is really simple. It's just similar to the secant method. So once you have this inputs, the steeply descent method will run in this way. So they will run this k is the iteration number, is from 0, 1 to up to the maximum iteration number you set here. And during each iteration, what you're going to do is you're going to compute the gradient. So for each xk, you're going to compute gk. So now I only have x0, so I'm going to compute the g0, which is the gradient f at x0. This is why I need to first compute this g by applying gradient f to x0. So remember that the gradient f is one of the inputs that you're supposed to know. So you can apply to the x0, you get the first g. And then once you have the g, you need to, the only thing that is left for this iteration, or the key for this iteration, to find out the step size. The step size needs to be the minimizer of this. Okay, so we have shown that, said before that this we can define, for fixed xk and gk, we can define this line search function that is a function of alpha, and it changes when this is function of alpha defined in this way. So this is how I define the line search function. I call the phi of a. For simplicity, I just call the variable a. Let me correct here. So for the given g and the given x, right now this is my g, this is my x. Okay, so it's like I have the x0, g0 here. Then I'm going to define my phi of a. A is like the alpha there. So phi of a is this function. So as you can see, this is a function of a only, because x0 and g are already computed. Right? The only thing that I can change is this a. So I'm going to evaluate, for every given a, I'm going to evaluate phi of a as the value of f at x0 minus ag. Okay? But what I really need is phi prime, because I'm going to apply the secant rule or secant method to minimize this function with respect to a. So I need to find the minimizer of this phi, a minimizer alpha that minimizes this phi. Okay, so it's a univariate function phi here that I can apply the secant method, but secant method requires the phi prime instead of phi. So to get phi prime, I need to know how to compute the phi prime. The phi prime on the left hand side can be computed by taking the derivative of the a on the right hand side, and by that I need to use the chain rule. So the chain rule gives me the phi prime of a as the gradient f at x0 minus ag, as you can see on the right hand side. It's just taking the chain rule, and the first thing I need to take, the first gradient I'm going to take is on the outside f, the external f, and then I need to take the derivative of a of the inside, which is giving me g. So I have the gradient f, I have the g. There are two vectors, and I need to make an inner product of them, okay, to get a scalar. So this scalar will be my phi prime at a. So I treat this as a column vector. I treat this as a column vector. So when I take the transpose over the first, here I'll get a row vector. So I have a row vector multiplied to a column vector, which gives me the inner product of the two. So this is actually giving me the inner product of two. So this is due to the chain rule, which is what we have explained in class. And then you get this phi prime. So this phi prime will be the function. The purpose of phi prime is that for any given a, you're supposed to know how to evaluate the phi prime at that given a. So this is the one of the requirement, or one of the inputs required by the secant method, if you recall. Okay. So now once I know what this phi prime is defined, I can try to find the minimizer of this function phi of alpha, which is this. Okay. I need to find the minimizer of this. So to find that, as required in the secant method, I need to give the phi prime, which is the one I already know how to do. So I give it to phi prime, and I also need to give two initials a0, a1. They're both scalars to the secant method, and I can also input the maximum iteration number and also the tolerance if I need. So just recall how we did for the secant method before. So once you apply the secant method here, then this one will require some iterations, inner iterations, right? Because you do, when you apply the secant method to minimize a univariate function, it takes some iteration. But whatever that does, it will give you, after they finish, it will give you this alpha. This alpha will be the step size you choose for this iteration, for the case iteration of your steeply descent method. So you get this alpha, and then you update your x0 by to the new x0. So the x0 will be the alpha 0 minus alpha g, which is like this. So you have the previous xk, you have the gk, and once you figure out this alpha k, you can use this formula to get the next xk. So my x0 will be updated to this. So this is the iteration. And the key is this secant method. You need to apply the secant method to Phi Prime and find this optimal step size in this iteration. And the optimal step size is obtained by minimizer as the minimizer of the line search function Phi, where this line search function is this. Okay? But to really compute the minimizer of this Phi using the secant method, we actually need to know how to compute the Phi Prime. So we define the Phi Prime here, and then use this as the input to the secant method, and then run the secant method as a subroutine or sub function that can give you this optimal step size alpha for this iteration. So once you finish these 4 steps, you can move on to the next iteration of the steady descent method, and eventually, after it terminates, you can get this optimal x. Then this x is a vector. This is supposed to be minimizer of this problem. Have implemented the secant method. That will be a subroutine used in the steady descent method. So here we're going to show how to implement the steady descent method and how to call that secant method as a subroutine. So this is just a continuation of the code I wrote earlier. Previously we have this secant method implemented, and now I'm going to implement the steady descent method. So recall the steady descent method is finding the minimizer f, which is mapping from Rn to R. And for this algorithm to work, we need to input the gradient of f. That is a function. For any given value x, it can help you to compute the gradient of f at that point. That's supposed to give you a vector. And it also needs an initial guess. We call it x0. This is the initial vector thrown into this algorithm. And after the iterations, the steady descent method will return the minimizer of f. Okay, you can also set the maximum iteration number as one of the stopping criterion, and also the relative change as another stopping criterion. We'll show that one later. So this is the algorithm. Okay, so I call this function steepest as a steady descent method. It requires a gradient of f. This is the function that I need to give it to it. I need to give to this algorithm, and also initial guess, which is supposed to be a vector. We'll assume all the vectors are column vectors here. And when you implement the vector, you make sure that it is a column vector as well. And then also you have you can set the default maximum number to 100, the default tolerance to be 10 to negative 3. Okay, then the main loop. Again, for k as an iteration number running from 0 to maximum iteration minus 1, you first compute the gradient. And then once you compute the gradient, the key step next is to find to do the line search. So first thing is you need to define what is a line search function. And as we showed earlier, we actually need to not just the line search function, we actually need to know what's the derivative of this line search function. So line search function, we used the notation phi earlier. Okay, and here I will call this line search function LSF, line search function. That is the phi that we used. The line search function is a function of a, and for given x and g, the value of line search function at a will be just f of x minus ag. Okay, so this is how I define the line search function as we showed. It's supposed to be an inner product of the g and the gradient of f at x minus ag. Okay, so it's supposed to be an inner product of g and the gradient of f at x minus ag. So now my current x is x0, my current g is this g that I just computed, so that I need to make the inner product of the two. The g is a column vector. This is what I said. The gradient f will return a column vector, return the gradient as a column vector. So this G is a column vector. So I dot T means that it's a transpose, it's a row vector now. And also the gradient F at this point, for every given A, I will compute the gradient of F at this point, and that's giving me another column vector. So I have a row vector here, I have a column vector here. I can make a product, matrix product between the two. It's a row vector, column vector. So it's like two matrices, and then multiply them together, it will give me a scalar, and that is the inner product of the two vectors. So the matrix multiplication is implemented as np dot here. Okay, so it's again a function in the NumPy package, and it will give you the product of two matrices. So this is what my derivative of phi looks like. So the D means the derivative of the line search function for every given A is going to compute this value and return it as the derivative of phi at A. Okay, so once we define this, we can call the secant method. This secant method is applied to minimize the line search function with respect to A. So the derivative of the line search function is the one I just defined here. Okay, so I'm going to use that as input, and I also need to give two initials. Remember that the secant method requires two initials. I gave them as 1, 2. You can give other two. So you just give two numbers. There, I use the 1, 2 as a default every time. And the 30 is the iteration number that I want, maximum iteration number I want this secant method to run. If I do not set this, then we'll be using the default number in your implementation of the secant method. And also this is the tolerance that I want to be 10 to negative 2 here. And once I apply the secant method to this, it will return the minimizer, or approximately giving me the minimizer of the line search function, and I call it alpha. And once I get the alpha, I will update x. Okay, this will be the new x. Okay, this will be the new x. So, and with this new x, I will see if it is making sufficient progress. And remember that here I'm going to, we can use the relative change as the criterion. To compute the relative change, I need to see the norm of x minus x0. I'm using norm instead of absolute value is because both x and x0 are are vectors. So this is under the linear algebra package, under the NumPy package. And within this, there's a norm function that I can evaluate the norm of a vector. Okay, so I'm using this to evaluate the norm of x minus x0, and also evaluate this, using this to evaluate the norm of x0. So the ratio of these two gives me the relative change of x compared to x0. Okay, and if it is small enough, we'll terminate this algorithm. Otherwise, we'll update this. This will be the x that we just computed. We'll assign this x to x0, give this x to x0. Okay, and in this case, we'll have computed this, I'll get a new x, and then it will return to the next iteration. We'll compute the gradient of f as this new x0, and then repeat the same thing. So once the maximum iteration number is reached, or the relative error is smaller than the tolerance, this loop will be terminated, and the x will be the output. Okay. The result of the implementation will apply to the test problem in the class. So this is the test 1.py. This is the Python script that I use to test the problem. Here I'm going to first, again, I'm going to import this NumPy as np. And also, this is the import the NumPy package. And also, I need to import the functions inside the ARG, which is the function I wrote. Right? This function here contains the two algorithms, the secant method and also the steeply descent method. So in this code, in this script, I need to import that because I'm going to use that two functions here. Okay, so here the problem that we define is a function of three-dimensional vector x, and to define this for every x I have, I'm going to extract the three values x1, x2, x3. So I'm going to extract the values of the vector x using this formula. So the x0, so Python always start the index by 0. The first argument is indexed by 0. Second argument is indexed by 1, and so on and so forth. So x0 will give me the first component, but it could be in the matrix form. So I need to actually extract the actual value of this x1. So I use this dot item. So this is a very special, because this problem is defined in a pretty strange way like this. So that's why the we need to do this. But for many larger problems, we don't really need to, get the values one by one. It's just for this example. So anyway, we get this x1, x2, x3 as the three components of the x vector, and then we can compute the y. Recall that the y is defined as x1 minus 4 to the fourth, x2 minus 3 to the square, and 4 times x3 plus 4 to the fourth. So this means the power. It's a power of 4. This is power 2 means this is squared. Okay, so you can easily compute this. So once we compute this, you get a scalar y. That is the value of f. So you plug in x, the f of x returns the value y, which is scalar. Okay, so now we need to compute we also need to define the gradient of f. So gradient f is for the function f that defined above. I'm going to compute the gradient of that function at any given x. So again, I'm extracting the three components, and then I need to form the gradient. I call the gradient g, which is also a three-dimensional vector. It's a three-dimensional vector, a column vector, or it's a 3x1 matrix. So I define here. So I initialize it as a zero vector, 3x1 0 matrix, and then the first component of this g is set to the partial derivative of f with respect to x1. So you can see only this first term is a function of x1. It involves x1. So when I take the derivative with respect to it, I get 4 times x1 minus 4 cube. So this is why I have this. It's 4 times x1 minus 4 cube. And also the g1 will be 2 times x2 minus 3, which is the derivative of this. So you can see it's x2 minus 3 squared. So I take the derivative, I get 2 times x2 minus 3. And similarly, the last argument gives me the partial derivative of f with respect to x3. Okay, so I have this, I fill in these three values or three components of g, and then I can return the g vector. Okay, so now let's actually run this algorithm. The initial is set to 4 to 1 as with any class. So I'm going to use this command or this row to define x0. That's our initial guess. And this is returning a row vector, but I want everything to be a column vector, so I reshape it to a column vector, 3x1 column vector. This command is called np.reshape. And I can print it out to see that if it's really a column vector. And then once you have this initial value, I can set the maximum number of iterations. I can set the tolerance. You can set to other numbers you like. And so I'm just going to use this. And then I will call the steepy descent method in the algorithm file I wrote earlier. So x will be lg.steepest. And remember that algorithm requires the gradient of f. That is something we have defined here. So I require that I defined. And I also defined the initial. I also defined the maximum iteration number and the tolerance. And then after running this x will be the output of steepy descent method, and then we can print it out. Okay, so let's just after this let's just run. Click run. You can, if you use the
anaconda, within which you just use it's a so-called spider. That is the default code editor in Anaconda. If you are using other editors, for example, the MS Code or anything else, you can usually you have this run button there, or you can also type this Python space test1.py. When you are in the terminal, you go to this folder here, wherever you store your code here. You just go to that folder and you type in Python space test1.py, and then press enter. It will give you the result. But for here, since we have an integrated editor, we just click it run. Okay, so I run it. I'll see this will be the result when I print x0. That is 4, 2, 1, which is a column vector, as you can see. And this when I print this x, I get that. So it's a 4, 3, negative 4.96. Okay, so that's the output for the stability method when I set this as the parameters. You can set other parameters. You can even ask the code to print out the result for each iteration. What you need to do is just for the stability method, after each iteration, you can ask it to print out what is x. For example, you can ask it to print out x0, and then that will print out the result after each iteration. Okay, but this is basically what you can do.
Okay, now let's continue with the stability method applied to a very special type of function called quadratic function. So a quadratic function, as we saw, the original quadratic function can be written in this way. For a given matrix A, n by n matrix A, and the n-dimensional vector B, you can define this quadratic function f of x. And this x is an unknown, it's a variable, it is an n-dimensional vector. So you can compute this value. On the right-hand side, you will get a scalar, right? The reason is you have a row vector here. The transpose of a column vector gives you a row vector, and then a matrix, and then a column vector. So when you multiply all of them together, you get a scalar. The second term, you have a row vector, which is B transpose. That is a row vector, and then multiplied to x is column vector. So you get a scalar as well. So you have two scalars. The difference of them is this f of x. So this is the general definition for quadratic function. But we showed last time that you can easily transform this into a standard form where you take the sum of A and its transpose. You define this to be Q. So I'm going to define the Q to be the A plus A transpose. I'm going to call the Q to be A plus A transpose. And then I can rewrite this X transpose AX as 1/2 of X transpose QX. And the benefit here is that this Q is a symmetric matrix. Originally, A doesn't have to be a symmetric matrix, but here, once I define Q in this way, then the Q will be a symmetric matrix. I do not change this B transpose X here. So this will be equivalent. This is an equivalent problem, exactly the same problem as this one. Okay, the goal is due to this relation between Q and A. Okay, so this is a very special type of function, but it has lots of applications in the real world. And today, we're just going to show what happens if we apply this stability method to it. Okay, so remember the stability method is using the negative gradient as the descent direction, and the step size alpha k is the minimizer of the line search function. Okay, and we will show this in details in the next slide. But first, we know that we need to compute the gradient of f, and for reference, we also can compute the gradient of the second order gradient of f, which is called the Hessian of f. Okay, so the gradient f and the Hessian of f. For quadratic functions like this, the gradient and the Hessian are very easy to compute. It's just they have closed formula, which are given in the bottom line here. Okay, so you definitely need to practice this or try to show this by yourself. You can do this in different ways. One way to do this is to just recall the original definition for this X transpose QX. So you have X transpose QX. Let's say the Q matrix is written as Q11, Q12, Q1n, and the Qn1, Qn2, Qnn. Okay, but this is a symmetric matrix, but it does also applies to non-symmetric matrices as well. If I'm going to, I'm just trying to show you what this one is actually is. So this is actually, let's show this, the x1, xn, and you have this matrix Q11, Q1n, Qn1, Qnn, and you have this original form, vector form of this column vector form of this X. And this is actually, you can show this is just xi times xj times qij for all the I and j from 1 to n. Okay, so you can see there you actually have n squared terms here. For I equals to 1 to n, j is also running from 1 to n. So you have n squared terms here. This is actually what the X transpose QS is. The B transpose X is pretty simple. So B transpose X is just B1. Suppose B1 through Bn are the components of B, and they will be just X1, Xn for the X. The inner this multiplication will give you the inner product between the two, which is B1 X1 all the way to Bn Xn. So there are n terms. Here, take the sum of the n terms. On the top, X transpose QX is the sum of n squared terms in general, right? Okay, so now you can see if I want to compute the gradient of f at x, then I need to compute the gradient of f, gradient of this with respect to x minus the gradient of this with respect to x. Okay, so these are actually the two terms. Let's say the second one. This is pretty easy to compute. So you know the gradient of B transpose X. The gradient is applied to a scalar, and that scalar is scalar is the value of B transpose X. Okay, and you remember that this is giving you the partial derivative. You should stack the partial derivatives of this B transpose X with respect to each component of X. So partial derivative with respect to X1, partial derivative with respect to X2. So you need to take the partial derivative of this with respect to X1. You put down the first argument, first component here, and the partial derivative with respect to X2, you get to the second component. But this is easy, as you can see. The partial derivative with respect to X1 will be just B1, since there is only B1 in front of X1, right? And the partial derivative with respect to X2 will be just B2, all the way to the last one. So here it's just B1, B2, all the way to Bn. And this is just the B vector itself. So the partial derivative, the gradient of this quantity with respect to x is just the B. Okay, so that's simple. And that is why we have this B here. Okay, the gradient of f with respect to the gradient of this B transpose x with respect to x is just B. Okay, now the question, the interesting part is here. How do we take the gradient with respect to this? Okay, so you can see there are two x there. If I apply the gradient, I should use the product rule. It's like two x is applied, it's at the same place, appear in the same term. So when I apply the gradient, I'll need to apply, let's say, the gradient of X transpose QX. So I first take a gradient with respect to the first X, and then multiply the second X. So when I take the gradient with respect to the first X here, you can see the X transpose QX. this is like a vector, this is like another vector, right? So if I treat this second vector as B, as the previous B here, so let's say this is the B. So this is the B. This is the same as B transpose X or X transpose B. They're the same because there's just inner product between X and this vector. So when I take the gradient of this, I will get just the B, right? That's what we showed earlier. B transpose X. When you take a gradient, it will just give you the QX. So actually, I will just get the QX here. This is what happens when I apply the gradient to the first argument, and then I get this. Okay, and remember that now I need to take the derivative with respect to second x as well. So to do that, right, I will need to treat this. I need to take gradient of this x, so I can put these two together, which is together is the transpose of the x transpose q is the same as q transpose x, and also transpose. So now this is like my B. This is like my B because this is the B transpose times this x here. So this whole thing is like the B transpose, and this is the x. So when I take the gradient with respect to the second x, I'll just get q transpose x. Okay, but remember that q is a symmetric, so the q transpose is the same as q. So I have just the 2qx, right? Q is equal to q transpose. So I get that. So that's why when I apply the gradient to this x transpose qx, I'll get 2 times qx. And I have another 1/2 at the beginning, in the front, so they cancel with the 2. It is cancelled with this 2 that I have. I'll have this qx left. So this is the one way to do it, or you can just apply the original definition of partial derivatives to this and also to this. The second one is still definitely giving you the same, right? You apply the partial derivatives with respect to each of xi's, you get this B. You can also do the same thing for this one, and you get the same result as we showed here. Okay, the partial derivatives with respect to each xi, and eventually you get this same q here. So that's how we get this gradient f at x. So for a quadratic function, the gradient of f is pretty easy to compute. You just have qx minus b, right? And the Hessian of f. So the Hessian will be the matrix of second order partial derivatives. So the Hessian originally is defined as the Hessian of a function f is actually fx1 df dx2 dx1, right? You know this partial derivatives xn x1, and all the way to the last one is df2 dxn squared. So this is n by n matrix. This is called the Hessian matrix. Hessian matrix. Okay, so you can apply that to this. So you already got this as your gradient f, which is the df dx1 all the way to df dxn. Right, this is your gradient, and this is a vector. This is a column vector, as you know. That's it, because this is a Q is n by n matrix. This is n by 1 vector. So you have this matrix times this vector gives you a vector, and this one itself is a vector. Okay, so it's vector minus vector. This is the gradient, and the Hessian is just to take the gradient of the first component and the second component all the way to the last component. And for each one, you compute the gradient, you get a vector and put it as the row, and that will be the first row of this matrix, which is this row here. Okay, it will be the first row of this Hessian matrix, and until your last one, you take the gradient of this with respect to x1 through xn. Then you get a bunch of second order partial derivatives. This will be the last row of this Hessian matrix, and you can easily show that this will be just the Q. Okay, so the second order derivative or the Hessian of this quadratic function, it will be just this Q here. Okay, so you need to practice this yourself. Convince that you repeat all the steps, and you really need to convince yourself, since this result will be used again and again in this class. Okay, for a quadratic function f given in this formula, you first need to do that. If it's given this formula, you need to convert into this standard form, and then given the standard form, when I ask you to compute the gradient and the Hessian, you need to immediately write down this. You need to know how to compute them using this. Okay, so next, let's say let's try to apply the stability descent method to this quadratic function. So here I require this Q to be a positive definite matrix. So I require the Q to be this, and the reason is really simple, because remember that the Hessian of this f is just the Q. Remember the second order necessary condition says that if you reach to a critical point where the gradient of f at that point is 0, then for this point to be a local minimizer, the Hessian matrix has to be positive semi-definite. Okay, and if you want it to be a strictly local minimizer, then this Q has to be positive definite. So eventually we will find that there will be only if the Q is a invertible matrix, then there will be only one critical point of this function. The reason is when you compute the gradient of f, and you get this and set it to 0 and solve for x, the solutions will be the critical points. But if Q is invertible, then the Qx minus b equals to 0 has only one solution, right? It will be just the x that makes Qx equals to b, and that x is just Q inverse times b. So there will be only one. And if you want this one, it's you only have one critical point. The minimizer has to be it. If you have a minimizer, it has to be it. And there you have to check the Hessian matrix is greater than positive semi-definite. That's why the Q has to be positive semi-definite. You want this minimizer to be unique, then the Q has to be, we need this Q greater than, it's a positive definite matrix. So this is just making sure that this one really has a global minimizer, and that minimizer is unique. Okay, so we're considering the case that Q is positive definite. So later on, when we try to apply any optimization algorithms to a quadratic function like this, we need to make sure that Q is positive definite. Otherwise, we may not really find the minimizer, or there could be infinite many minimizers. So that's not the case we're interested in. Let's consider the case that Q is a positive definite matrix. Okay, so Q is a positive definite matrix, and it's also symmetric. Remember that. During this class, when we talk about the positive definite matrices or positive semi-definite matrices, we always assume that they are symmetric. Okay, so when we say positive definite matrix, like this, positive definite or positive semi-definite, we always assume that this matrix is symmetric. But in general, in some books, they will distinguish the positive definite matrix and the symmetric positive definite matrices. They think these are two different things. Because if you define the positive definite matrix as when the matrix A is positive definite, means that X transpose QX is greater than 0 for any X non-zero. Okay, semi-definite is the X transpose QX greater than or equal to 0. It doesn't matter what X is. So X could be 0. X is 0, then it definitely is 0. But if X is non-zero, you could still get 0, but it cannot be negative anyway. Okay, so this is the definition for the two. If you use this as a definition, then the Q doesn't have to be symmetric. Okay, a simple example is that, say I have a matrix, a Q. I say I have a matrix that's written in this way. then you can easily check this is a positive definite matrix. The reason is, say I have X transpose AX. So remember this A is not symmetric. So I multiply the X on the two sides, X1, X2, and have this 1, 1, 0, 1. I have X1, X2. Then I'll have, if we compute this, you find out this is just X1. Let me show you the actual steps. So I multiply the matrix and the last X first. You have X1 plus X2, and X2. And then when I multiply the two together, I'll have X1 squared plus X1, X2 plus X2 squared. And I know that this must be positive unless X1 and X2 are both 0. The reason is this is just equal to, I extract 1/2 X1 squared and leave another X1 squared here, plus X1, X2 plus 1/2 X2. Again, I split X2 squared to two equal parts. Look at this. So you can see this X1 squared is split into two. Also, this X2 squared is split into two equal parts. And now these three terms together completes a square. Right? These three terms together is just 1/2 of this middle term will be just 1/2 of X1 minus X plus X2 squared. And you still have this X1 squared plus this X1 squared, X2 squared. So you can see this. Oh, sorry. Both of the three terms are non-negative, so this has to be greater than or equal to 0, and it is 0 if and only if X1 and X2 are both 0. Right? So for any non-zero X vector, if any of either one X1 or X2 is non-zero, this cannot be 0. So that's why this A matrix is symmetric. It's a positive definite if you're using this as a definition. It's a positive definite matrix. Okay, so because X transpose AX is always greater than 0 for non-zero X. Okay, but this A is not symmetric. Okay, so that is a subtle difference between symmetric positive definite matrices and positive definite matrices. But in this class, we do not distinguish them. We always use the, when we refer to a positive definite matrices, we'll always assume it is symmetric. The reason is similar as in the previous slide. We can always define Q to be A plus A transpose. And then if A is positive definite, then Q will be symmetric positive definite. All right, so that's the starting point. We're given this quadratic function with a positive definite, symmetric positive definite matrix Q and a vector B. And according to what we derived earlier, the gradient of f at a given xk, which we call the gk, is just the qxk minus b. So xk, gk are, once you're given the vector xk, you can compute the vector gk using this formula easily. Okay, and so this is the gradient step. So remember that to compute or to use the steeply descent method, we need to compute the gradient. We also need to figure out the step size. The step size is supposed to minimize the line search function. So for the kth iteration, given the xk and gk, the line search function is this. So we define the line search function phi alpha in this way. So for every given alpha, you compute a value using this formula. Okay, so this is only a function of alpha since xk and gk are given, already computed. And now, because f has a quadratic form, so this is the f, right? So I just need to plug in the xk minus alpha gk into this f. I can compute the phi alpha. So let's do that. To plug in xk minus alpha gk into f, I will just replace the x here by this, and I will going to replace x here by this. So this is my argument here, and also minus b transpose times this. Same thing here. All right, so now you can see this. An easy way to, so now where I'm trying to find out the minimizer of this phi alpha, where phi alpha is defined in this way, I know that I just need to take a derivative, set to 0, and see what I get. Right? This is supposed to be what I get are supposed to be the critical points, and the minimizer should be one of them. So now let's take the gradient or the derivative with respect to alpha. So that means I need to take a derivative with respect to alpha for the right hand side. How to do that? You see the alpha appears here, here, and here. So I just need to take the derivative with respect to alpha one by one. All right. So to take a derivative with respect to alpha, for example, the simplest one is this one. Right? When you take a derivative with respect to alpha, you know that in front of alpha, this is B transpose GK. So the inner product of B and GK gives me the coefficient in front of alpha. And I have these two negatives, so together it should be positive. Okay, so that's how I get this term. So this is a scalar in front of alpha for this. Okay. Similarly, I can take the gradient with a derivative with respect to alpha for this term, and you see that you can show it by yourself that the derivative with respect to derivative of this term with respect to alpha will be just this. Okay, so you can either do this or you can apply the formula we had earlier. Remember that the phi prime of alpha, if you define your phi alpha in this way, the phi prime of alpha is supposed to be gradient f of x k minus alpha gk transpose the gk, right? And remember, what is gradient f? Gradient f, if you have any argument inside, the gradient f will be just q times that argument minus b. So that means this first term is nothing but q times xk minus alpha gk minus b. That is the first, that's the gradient f of at this point. Then transpose gk. Right? So that's the phi prime. And sorry, you have a negative in the front. So I have a negative in the front. So that's this. And then you expand this, you get this term. Or you expand this, then you get this term. Okay, so solving the minimizer of phi is we can take the derivative of phi with respect to alpha, we get this, and set to 0 and solve for alpha. Now we get this, we set to 0, and we try to solve for alpha. So you can see there's only one alpha here. So let's just, you can solve it easily. You move this, for example, you move this to the right hand side, and you extract every term about alpha on one side and everything else on the other side, and you solve for this alpha. You see that in front of alpha, this is it. And anything else is this term times that plus this term. So I can move it to one side, and eventually you get this. This is the alpha k. Okay, so it's just by solving the alpha from here. And once you have this term, you can see this is the qxk minus b, and that is supposed to be the gk, right? It's the gradient f at xk. So this is just gk. So what you have on the numerator is nothing but two gk's. The inner product of gk and itself. And denominator is gk transpose qgk. Okay, so unlike in the general case, for a quadratic function f, the gradient is easy to compute. It's just the qx minus b. Not only the gradient, but also the best step size, the steepest step size, alpha k, can be directly computed. There's a closed form for that. You don't really need to do this minimizer, because for this case, the minimizer has a closed form. And that closed form is this. So you can just, once you get the gk, you can put this gk, for the numerator, you got the inner product of the gk with itself, that gives you a scalar. On denominator is gk qgk, which gives you another scalar. So a scalar divided by another scalar, and that is your alpha k. That's the optimal step size. Okay. So now it's clear. if you want trying to apply the stability descent method to this quadratic function, then for each iteration you have the xk, you can compute the gk in this way. This will be your gk, and then you plug gk into this formula, you get the alpha k. Now once you have the alpha k gk, you can update the xk to xk plus 1. Okay, so in summary, the stability descent method, when you apply it to the quadratic function here with a positive definite matrix Q, then for each iteration you just need to do this. Okay, so this is the gk, this is the alpha k, and they all have closed forms.